Friends, let us resume where we left off in the previous lecture. Now, in the previous lecture, we considered one of the technique that is involved, or that is an integral part of communication, but it does not do, or it does not operate in a way rest of these techniques work. In a sense, we considered in our previous lecture a process or technique called as screening, and screening is quite different from other techniques that are involved in the process of communication. If you consider the overall flow chart or the process chain involving communication, the entire scheme of things can be categorized into crushing and grinding. So crushing involves different stages, and it is the initial part, or it constitutes the initial part of communication, whereas the grinding, it constitutes the finer and the final part of the communication. In between these different stages, in between these different techniques, we have a unique process called as screening. And here, unlike crushing and grinding, wherein essentially the sizes of the mineral particles are reduced, the sizes of the minerals are reduced. In screening, what is essentially done is, depending on the size of the particles, these fragments are being separated. So depending on the size, these fragments, these yield of the different fragmentation process, the yield of the crushing particularly is separated, and depending on the size of the particles, it is either fed into grinding or it is further reduced through crushing. So this is what screening essentially involves. Now, in the previous lecture, we saw that given that screening follows a specific modus operandi, it follows a specific approach, different ways of separating or different sections wherein the particles are separated based on their sizes can be categorized as a whole as screening. So even though screening essentially involves, or screening occupies a specific position in the overall process chain of communication, given that the way the screening is achieved, the way the particles are differentiated based on, the particles are distinguished based on the sizes, is rather straightforward, or it can be related to several other techniques that are involved in the process of communication. Different techniques or different events that are involved in the overall mineral processing can be categorized as screening. So screening conventionally occupies a specific position in communication alone. However, because of the undergirding technique, several events or several processes are being categorized under screening, and one, apart from the conventional process wherein the particles that is rendered by the communication is segregated and then fed into grinding or further crushing. So this is the conventional form of screening. Apart from that, we have scalping. So just to recollect, the difference between the conventional screening and the scalping is that in case of scalping, we are primarily interested in, or the yield that we get out of the scalping is the large size run-of-mine particles, and the smaller particles that are significantly or that vary significantly in their sizes, they are collected separately and fed directly into appropriate communication process. They can directly be fed into secondary, tertiary or grinding process. However, the primary intention of scalping is to gather out the major portion of the large run-of-mine particles, which are in the range of meters. Now, in addition to the conventional screening and also scalping, we use the process of screening in order to separate the mineral particles that are significantly reduced in size. So these mineral particles are quite difficult to handle, and while they are being transported, they cause environmental pollution. So in order to avoid all this, we separate these fine particles, these other significantly smaller or considerably smaller particles, undesirably smaller particles, and these are referred to as fines, and we use a process that adapts the methodology of screening to separate these fines and also the dust. So the difference between fines and dust is their chemical composition. In fines, what you essentially have is the fines, they essentially comprise of, or they constitute the chemical composition that are found in the actual minerals. However, in case of dust, they are external agents, they do not constitute, or they are not part of our mineral. So both fines and dust are separated using an approach that is similar to that of the screening, and therefore we attribute them or we categorize them under screening. And the same goes for separating the grinding media. So once we are able to we arrive at the yield of the grinding process, once we are quite sure that the amount of reduction, this reduction ratio that we desired through the yielding or through the grinding process is achieved, then we use a technique that is similar to that of the grinding in order to separate the grinding media from that of the mineral particles. So similar to the dust, which is an external agent that is found in the mixture of minerals that are rendered by the different comminution processes, the grinding media are also an external agents. However, the dust, they play rather a detrimental role, whereas the grinding media, they play a significant or they play a critical role in a particular process of the comminution. However, their role is rather limited to that grinding process, and therefore they need to be removed after the desired reduction ratio is achieved. So this removal of the grinding media is done by a process that is similar to that of the screening, and therefore it is also categorized under screening. So conventional screening occupies a specific position in the process time, whereas owing to the similarity in the process that is being adapted, the similarity in the methodology that is being adapted for several other techniques, all these different techniques are categorized under screening. These include scalping, removal of fines, dust, and grinding media. Now, the underlying similar process or similar methodology that enables us to categorize all these different techniques as screening is the one that is described here. So what we essentially have is a schematics of how a screening works. In case of screening, what you essentially have is an inclined table, and in this inclined table we feed in our particles that needs to be separated based on their sizes. The table that we feed these particles onto, they are perforated, they are not completely solid, they are perforated, and these perforations, they have a specific size, and we refer to them as apertures, and we allow these feed to pass through this perforated table. And the reason it is inclined is, one, we want to allow the particles that are greater than the size of the apertures to be collected on their own. We don't want to introduce a special technique in order to gather the particles that are greater than the size of the apertures. This way of inclining the table enables us to do so. Now imagine if you are operating on the large scale, if you are operating or using this technique in case of scalping, then the particle that you need to gather out that are on the surface of the table, they are huge. Therefore, when you don't have an inclined surface, when you have rather a completely horizontal surface like you have in case of sieving, in those cases you would need huge or heavy duty machineries in order to separate these large run-of-mine particles alone. So therefore, in order to have a technique, in order to have an approach that allows us to collect the large size particles on its own, we have this inclination here. And secondly, the process of separation, the way the smaller particles they pass through the table, involves an interaction between the particles and the surface of the table. So all the particles that you feed in needs to interact with the surface of the table in order for the screening to occur. The inclination of the table allows us to do so. So therefore, we have, in order to serve these two purposes, we have the inclination of our table. Now secondly, in order to ensure that the interaction between the particle and the surface of the table is efficient, we include vibration in the process of screening. So the methodology is characterized by two unique attributes. One is the inclination of the table, and other is the vibration of the table. The inclination, it allows for the collection of the large size particle, and to a certain degree it allows for the interaction of all the feed particles with the surface of the table. The vibration predominantly ensures that all the particles they efficiently interact with the surface of the table, meaning they efficiently interact with the openings or the apertures. Now the screening process as a whole, so all these discussions so far, all these have been rather oriented towards the operation of the screening process. Now if you consider what are the events that are occurring from the perspective of the particles that are fed into the screening. So these include stratification. So stratification is nothing but it is the interaction between the different particles, the particles of different sizes, which ensures that all the particles, they interact with the surface of the table, the surface of the inclined table. Because of the size of the particle, because of the shape of the particle, it is possible that certain particles, they occupy the surface, they are essentially placed, or they are easily placed on the surface of this table. So when you feed in, because of or owing to the size and shape rather, certain particles, they normally or they naturally occupy the surface of the table. Now this specific occupation of certain particles hinders the interaction of other particles with the perforation. So so the stratification, it ensures that these particles, after their interaction, they are moved aside, and the particles which are not naturally available to the surface of the table replace their position. So what we mean by stratification is essentially, because of their characteristic size and shape, you have, once you feed in your input, certain particles, usually large size particles, they occupy the surface of the table, and it is the smaller size particles that are found on the large size particle. They rarely get a chance to interact with the surface of the table, and only when they get the chance to interact with the surface of the table, they will be able to go through the perforations. However, because of their characteristic shape and size, the large size particle often occupies, in most cases they often occupy the surface of the table. Now what stratification involves is, it involves the interaction between these different particles, that is large size and small size particles, in such a way that after sufficient interaction of these large size particles, the small size particles, which are not naturally favored to interact with the surface of the table, are allowed to interact, and this is rather achieved by vibration. So the stratification essentially is the interaction between the particles of different shapes and size, and what it essentially ensures is the particles which are smaller and irregular and even spherical, which are not naturally favored to occupy the surface of the table, which are not naturally favored to interact with the perforations, are being forced to interact with the perforation, are being helped to interact with the surface of the table, are being rather enabled or facilitated to interact with or reach the surface of the table. So that is what we mean by stratification. And separation is the outcome of the interaction between all the particles and the perforations. So when stratification is interaction between the different particles in order to reach the surface of the table, separation is the outcome of this initial interaction, and separation essentially involves the interaction between the surface of the table and the particles. So in separation, what essentially happens is, the particles that are lower than the size of the aperture, they fall through, and that are greater than the size of the aperture, they stay above the surface of the, or they stay on the surface of the table. So that is essentially what we have, or what happens when you consider the behavior of the different particles that are fed into or that are considered or that are screened. So you have stratification, interaction between the particles, and you have separation, the interaction between the particles and the table. Now when you consider this overall process of screening, this process is rather based on these events of the interaction between the particles and the interaction between the particle and the table. So it is not rather a definite process, like you cannot definitively say, okay, when I have a particle of this size and this shape, it will directly interact with this particular aperture at this particular time, and it will interact and it will fall off in this place here. You cannot make a definitive statement on how a particular feed that you provide and what the particular particles that constitute the feed interact with these apertures and where they would separate. So we cannot give a definitive description of how and which particles will relate or will react with or will interact with the table, and how and where they will separate, or if they will separate. So all we can do is we can give a probabilistic statement on how the screening occurs. Of course, it is possible for us to state that given the specific size of the aperture, the particles greater than the size will stay on the surface and the rest will fall down. That we can state that definitively. However, what we cannot do is we cannot say that all the particles that we feed in will behave in this manner, because all the particles that we feed in needs to interact with the aperture in order to do so. So even though it is possible for us to claim that the particles that are greater than the size of the aperture stay on the surface and the less than the size of the aperture will fall out, we cannot definitively say all the particles will behave in this manner, because we need to ensure that the interaction allows for the particles with the lower size to reach the surface of the table, and even after reaching the surface of the table they are allowed to interact with the apertures and they are able to pass through this aperture. So even though it is possible for us to generalize the overall operation of the screening, we cannot definitively talk about a specific. We cannot definitively assert that all the particles that are less than the size of the apertures will go through. So therefore, what we essentially have is the whole process of screening is rather probabilistic. So we need to understand that given the behavior or given the interactions that are involved during the process of screening, we are not in a position to give a definitive statement, or we are not in a position to give a definitive description or definitive outcome of the process of screening. It all depends on probability. So it all depends on the probability of the interactions. Now, in order to ensure that there is the relatively high probability of the screening event, the probability of this interaction, both the interaction between the different particles and the interaction between the particle and the surface of the table is quite high, there are possibility for us, there are several parameters that we can control in order to ensure that this probability of interaction that ultimately governs the screening is high. So in order to do that, first we need to understand what are the factors, the parameters that govern the probability. So the reason we need to talk about the probability is primarily because we won't be able to give a definitive statement of how each and every particle will behave when it is fed onto or when it is screened, and therefore we need to go for a probabilistic approach. Now when we go for a probabilistic approach, we need to know what are the parameters that govern this probability. So once we are able to understand what are the parameters that govern the probability, then we will be able to rather devise our screening process in such a way that this probability increases. So our ultimate goal is to increase this probability of interaction. So this interaction, so we have an S here, meaning we need to increase the probability of both stratification and separation in order to ensure that we sufficiently screen our feed. So in order to do that, we need to understand what are the parameters that dictate the probability. So one parameter that dictates the probability is of course the size of the different particles that we feed. So the size of the feed or sizes of the feed. So our feed comprises of the different particles, and the way these particles interact with each other and the way these particles interact with the table, it depends on the input, that is the size of the feed. So supposing if you want to develop a model that talks about the probability of the interaction and the probability of screening, we need to include this particular parameter that talks about the different sizes of the input. Secondly, the other factor that governs the probability is the aperture. Now, the aperture is a critical factor that helps us give the definitive statement, that is, when the size of the particles is greater than this particular value, it will stay on the surface of the table. If it is smaller than this particular value, it will fall off. So while giving such a definitive statement, while giving such a generalized statement, there is a specific role played by this aperture, and the same role is played when we are considering this probabilistic approach, or when we are considering or taking this probabilistic approach to express screening. So both these statements, both the definitive statements and the probabilistic statements are the same. However, in case of the definite statement that all the particles that are greater than the size of this particular aperture will stay on the surface, such statement, it is generalized, it does not say anything specific. However, the probabilistic approach talks about what happens physically, what happens realistically. So it's not a generalized, purely theoretical statement. It is when you talk about in the case of a probabilistic statement or probabilistic, when you take a probabilistic approach, you are talking something in terms of the real world. And even similar to that is that the way we describe the generalized statement, we also need to consider the size of the aperture in order to describe the probabilistic interaction between the particles and the table and the screen that we have, that is this inclined table that we have. So therefore, in addition to the sizes of the feed, the sizes of the fragment, the aperture of the table also plays a critical role in the interaction that ultimately leads to the process of, that ultimately gives us the screening process. So the interaction, it comprises of the stratification and the separation. So when you consider the size of the field, it involves both in stratification and separation, whereas the aperture, the second factor that governs the probability of the interaction, it depends on the aperture, that is the opening of the perforations that you have on the surface of the table. So the third factor that essentially governs the probability of the interaction is the wire diameter. Now this factor is something that is rather quite new or quite important only when you consider the probability of interactions. So when you consider the definitive statement, the generalized statement, it involves both the size of the particles and the aperture. So when you consider the screening as in general terms, when you discuss screening in general terms, even in general terms, you need to include these two factors, that is the size of the feed or the size of the particles and the opening of your perforations or the aperture. So both these play a role, both these factors play a role both in generalized approach or generalized discussion and also in the probabilistic discussion. Now one factor that does not play a role in the generalized discussion is the wire diameter. So what we mean by wire diameter is, so supposing if you have a table of this sort, and in order to have apertures, what you need to introduce is you need to have include like perforations in these table. So in order to have apertures or openings on the table, you need to punch holes. Let's say you need to punch holes on this solid table. Now what the wire diameter means is that this region that separates the perforation, that separates the aperture, is what we mean by wire diameter. So here is rather a schematic consideration. What we have done is we have considered a completely solid table and we have punched in some holes, and these holes are nothing but the perforation that acts as the aperture and the distance between. So imagine that these holes are rather regularly punched, and the distance between these individual perforations is what we mean by wire diameter. Now depending on the position of these perforation, depending on the density of these perforation, these wire diameters vary. Now when you consider the generalized description of screening, you do not include these wire diameter. However, when you consider the probability of interaction, both stratification and separation, you need to consider the wire diameter because they are the integral part. They are also an integral part of your screening table. Your screening table not only comprises of these perforations or holes, they also comprises of the region that separates each and every perforation, each and every aperture. So these regions that separate each and every aperture. So if you zoom in to this section of the screening table, what you essentially have is two perforations of identical sizes, identical size meaning identical diameters, so similar apertures. So they are separated by the table, and this is what we refer to as the aperture. So they are separated by a specific material. So they are separated, and here in this case they are separated by the table itself, and these are referred to as the, and these are rather termed as wire diameter. Now in this example or in this schematic consideration, the wire diameter doesn't make much sense. However, if you consider the way a screening table is actually built, it is comprised of the way the screening table is actually built. It is built by considering the wires that are being attached across the surface of the table. So essentially what you have is, you have the table and you have different wires that are attached to this, to the ends of these tables. So essentially what you have is, when you have such wires that are meshed all through the surface of the table, so you have perforations, 1, 2, so on and so forth. You have these perforations, you have these apertures, and you have these wires. So essentially here in this schematic consideration, we have punched holes in order to separate one aperture from another aperture. But in realistic cases, what we essentially have is, we create these apertures, we create these perforations by creating these meshes using wires. So in the actual cases, in physical instances, what we essentially have is, these screening apertures, these screening perforations, they are created by meshing, by introducing different wires, and these wires, they have a specific diameter. So as the diameter increases, the distance separating two different perforation increases. So therefore we need to include the wire diameter when we are considering the probability of interaction. So essentially when we are considering the probability of interaction, the interaction involves again both the interaction between the particles and the interaction between the surface and the particles, and the surface comprises of perforation and also the sections that separate the perforations. So these sections that separate the perforations are here. So here in the schematics we have shown that this schematics we just included just to show the difference between the perforations and the section that separates the perforation. But if you consider the actual build of the screening table, the sections that separate the perforations are nothing but the wires that help build the perforations. So in case of the realistic screening table, what you essentially have is, we use wires, we use meshes in order to build these perforations, and depending on the thickness or the diameter of this wire, the section that separates these perforations vary, and therefore these needs to be included while we are discussing or we are formulating or taking a probabilistic approach for the interaction. Now the reason is, to simply put, there are three critical factors that govern our probabilistic approach to describe the screening process. Now we saw that, or it is rather we can conceive that the process of screening, even though it can be in a generalized manner, it can be described in definitive terms, it is far from being definite, because the screening process involves two different interactions. One is the interaction between two different particles, the particles that are fed into the screening, and the second interaction involves the interaction between the particles and the surface of the screen. Now when you consider the interaction, both these interactions, the role of the size of the particles is quite pivotal. So depending on the role of the size of the particle, these particles either can take up a position on the surface, or it can take up a position above the surface, which is found above the surface of the underlying particles. So therefore the interaction between the particles themselves depend on the sizes, and in addition to depend on their sizes, and in addition to that, the interaction between the particle and the screen on the screening surface, it depends on both the surface or the size of the particles and the aperture. So this interaction between the size of the between the particles and the aperture, that is the opening, and this is again, this can be described rather in a definitive manner, again based on the size of the aperture and the size of the particles. Nevertheless, the probability approach depends on how much or how far a given particle is allowed to reach the surface and is allowed to interact with the aperture. And finally, we need to also consider the wire diameter, primarily because the surface not only comprises of the perforations or apertures, the surface essentially includes the wires that bring about the perforation. It is the wires that essentially constitute, or they essentially bring about these apertures on the surface of the screen. So therefore, whenever we are talking about the interaction, in addition to the interacting with the aperture, in addition to interacting with the openings, during screening, the particles that you feed in also interact with the wire diameter. When you have a setup wherein the interaction between the particle and the wire diameter is quite huge, then the corresponding interaction between the particle and the aperture will be reduced. So therefore, there is an interplay between the particle interacting with the perforation and the particle interacting with the wire diameter. So therefore, whenever we are taking a probabilistic approach to describe the process of screening, we need to consider all these different factors. Now, the reason we need to consider these factors here is primarily because we want to increase the probability of interaction so that the screening that we are interested in occurs more efficiently. So we are able to achieve the desired screening. So we need to increase this probability of interaction. Now, one thing that cannot be rather fixed, or that is out of our control, or that cannot be rather varied in order to achieve our desired screening, is the size of the feed. The size of the feed, it depends on, or it is the outcome of the combination process. Now, if you want to dictate the size of the feed, again you need to do the you need to separate it based on the different diameters of the particles, which again goes back to screening. So essentially, one factor that is not in our control is the size of the feed. So size of the feed is rather given. The different sizes of the particles in a given feed is rather given. So therefore, we don't have much role to play when we would want to increase the interaction, the probability of interaction. However, what we can do is we can ensure that irrespective of the size of the particles, these particles are allowed to spend sufficient amount of time in a given portion of a screen. So the size of the feed is rather given. So we are not able to control. Supposing you are as an engineer, as an operating engineer, if you are handling a screening process, you have no say in what the particles are being fed in. You have no say in the different sizes of the particles that you will be feeding into the screening process. However, what you can do is you can ensure that you can create or you can devise your screening process in such a way that irrespective of the size of the particles spend sufficient amount of time on the surface of the screen so as to increase the probability of interaction. So one way of increasing the probability of interaction is by increasing the time of interaction, or increasing the time the particles spend on the screen. So for any given distribution of sizes, for any given feed with varying sizes of or fragments of varying sizes, by increasing the time these particles spend on the surface of the screen, we can ensure that we are able to achieve, or we are able to enhance the interaction, both the particle-particle interaction and the particle-screen interaction. So this, instead of varying or instead of playing around with the size of the feed, we are ensuring or increasing the probability by increasing the time that is spent by these fragments on the surface of the screen. One way of doing it is, so when we want to increase the time the particle spends on the screen, if you want to increase that, one way of doing it is reducing the amount of feed. So what we have is, we have established that screening is a probabilistic process, and in order to ensure that despite it being a probabilistic process, we want to have a desired amount of screening that needs to be achieved. We don't want to have a screening process that is not meaningful, that is immaterial. We want to have a screening process that is that enables us to separate the particles of different sizes. In order to achieve that, we are ensuring, even though it is a probabilistic process, we want to ensure that the probability of screening is higher. So it means we have to ensure that the probability of different interaction between the particles and interaction between the particles on the side is high. So one way of doing that is to ensure that the particle spends sufficient amount of time on the screening surface. It is not that once you feed in, or rather once you feed in your particles, they immediately come out of it with only negligible amount of screening, but we want to ensure that the particles spend sufficient amount of time on the surface of the screen so that the probability of interaction is increased. And in order to do that, what we essentially have is one way of doing that is reducing the amount of feed. Now when you reduce the amount of feed, what essentially happens is, it is quite rather straightforward for us to conceive. The movement or the particles over the surface of the screen will be reduced. So when you reduce the amount of feed, the movement of these particles on the surface of the screen will be reduced. So when the movement of the particles on the surface of the screen is reduced, essentially what you are doing is you are increasing the interaction between both particles and also the particle surfaces. Now when you consider on an industrial scale how this interaction occurs or how the feeding occurs, so this feeding, the event of feeding, is calculated weight per hour. The feeding that we are discussing right now, it is estimated by considering the amount of material, the weight of material that is being fed onto the screening table per hour. So usually it is, or the amount of material that is fed per unit time. So it is amount of material that is fed per unit time. So amount of, so when you consider the feeding, what you essentially, the way you quantify it in case of the screening process is the amount of material that is fed in per unit time. This amount of material is usually calculated in terms of weight. So therefore often it is tons per hour. So this is the unit of the feeding. Now when we say we are reducing the amount of feeding, so we are reducing the amount of feed, what essentially we are doing is we are periodically feeding a specific amount of material for a specific amount of time. We are continually doing it. However, the amount of feed that you provide, the amount of material that you provide is rather reduced. So that means the time taken for the material, for a given small amount of material to reach the end of the screening surface is reduced, and this reduced time, or rather it is rather prolonged, so when the amount of feed that you provide to the surface of the screen is reduced, then the amount of time that is spent by these feed on the surface of the screen is rather prolonged, because these feed, they have to travel all the way along the surface of the screen in order to reach the bottom of or the correcting bin. So when you allow, or when this travel, or when this transition of these particles, these feed to is rather prolonged, when they are prolonged, what essentially you have, you increase the interaction, you increase the probability of interaction, or you ensure that a sufficient amount of time is spent by the particles on the surface of the table. And when you have particles spending sufficient amount of time, then essentially the probability of interaction increases. So the probability of interaction not only between the particles increases, the probability of interaction between the particle and the perforated screen increases, so thereby allowing or increasing the chances of screening. Now here you also need to understand that the output that we get, the output feed, the amount of output that we get when you feed in a specific amount of input or the specific amount of particles, the output that we get, it also depends on the feeding rate. So it is rather straightforward to understand that depending on how much, or depending on the rate you feed your input, it governs the rate at which you get your output. So when you, in order for the sake of increasing the interaction, when you significantly reduce the amount or the rate at which you feed in your particles, your output will also be significantly reduced. So therefore, when you consider the efficiency of the overall operation, it will be lowered. So therefore, we need to achieve a right amount of balance. A right balance need to be achieved such that you are increasing the probability of interaction, but you are also ensuring the overall efficiency of the process. So in order to do that, we need to also mind the rate of the output. We need to also consider the rate of the output. The rate of the output should not be essentially lower, or it should not be considerably lower so as to affect the overall process. So even though reducing the amount of feed increases the probability, it also has an adverse side effect that it reduces the rate of output, meaning it also reduces the overall efficiency of the operation. So this technique of increasing the probability through reducing the amount of feed. So this approach of reducing the amount of feed in order to increase the interaction time, in order to increase the probability of interaction, is rather limited because it ultimately affects the efficiency of the mission. So therefore, one other way of increasing the probability is by operating or by appropriately devising the inclination angle, the angle of inclination. So you have, this is your horizontal surface and this is your angle of inclination. So this angle of inclination is associated with the screening table. So inclination of the screening table, the angle of inclination of the screening table. So we are considering the probability of increasing the interaction, and we want to achieve or increase the probability of interaction by ensuring that the time spent by the particles on the screening table, on the screening surface, is increased. So by increasing the time spent by the particle on the screening table, we want to increase the probability of interaction, thereby ensuring that the desired screening is achieved. Now one way of doing that is reducing the amount of feed. Now reducing the amount of feed is quite effective, but it also impacts, or it also negatively affects the amount of output. Therefore the overall efficiency of the mission is stunted. So even though reducing the input feed, the rate of input feed is effective, it has some negative effect. So we cannot extensively rely on this particular approach of increasing the probability. We cannot extensively rely on keep on decreasing the amount of input feed so as to increase the probability of interaction, because it affects the overall efficiency of the screening. So one other approach that can be considered is the angle of inclination. So when you consider the angle of inclination, meaning how steep your screening table is inclined, when your screening table is close to horizontal, then essentially what you have is you increase the probability of, or when you increase the amount of time the particle spends on the surface of the table. So when the angle of inclination is less, so when the angle of inclination is less and close to the horizontal surface, this ensures that the time spent by the fragmented particles on the surface of the screen is higher. However, we have a similar difficulty that we faced while reducing the amount of feeding in, because the reason for having the inclination is to ensure that the particles that are greater than the size of the apertures are easily gathered at the end of the screening process. Now, when you reduce the angle of inclination, when you consider the lower angle of inclination, such collection of the particles that are greater than the size of the apertures becomes quite difficult. So even though reducing the angle of inclination ensures that the time spent by the particles on the surface of the table is increased, what essentially we have is the overall process is interrupted in one way, that is the larger size particles, it becomes difficult for the larger size particles to get collected at the end of the screening process. Now, if on the other hand, if we increase theta in order to in a way that is greater than the desired value, when we increase theta, it is also possible that we increase the time of interaction, and it is also becomes a case wherein without sufficiently interacting between the without sufficient interaction between the particles themselves and the particles in the screening media, the particles they end up getting collected at the end of the screening table. So we need to have a right balance between the angle of inclination that is associated with the screening table. When you have a row angle of inclination, of course you increase the degree of interaction. However, the process itself will get the duration of the process itself will get prolonged, because the larger particle, the large size particle, they take enormous amount of time to get collected at the end of the table. Now, in order to enhance the collection of the larger size particle, in order to speed up the screening process, if you incline, or if you make the surface, if you make your table more steeper, then what you end up doing is you end up introducing or inadequate interactions, and thereby there is not sufficient degree of screening that is experienced or that is achieved by this process. However, you collect all these particles at a quicker pace. So again, similar to that of the feeding rate, you need to ensure that the right balance is achieved in the angle of inclination. Higher inclination, not much interaction, so not much screening. Lower inclination, even though the interaction is ensured, even though the time spent by the particle on the surface is higher, the longer duration is spent, but the overall process is again stunted. The efficiency of the overall process is stunted because the output rate is significantly reduced. The other way of increasing the probability is using the vibration. Now, the vibration, like we saw in our previous, while we consider the different events that are involved from the perspective of the individual particle, the vibration ensures both the interaction between the particles, and ultimately it also facilitates the particles that are naturally not inclined to interact with the surface, and it gives us opportunity for such particles to reach the surface. So vibration, it improves the interaction between these particles such that the smaller particles are allowed to reach all particles are allowed to reach the surface of the screen. So essentially, vibration, as when compared to the feeding rate and the angle of inclination, vibration has more of an advantageous effect over the process of screening. However, beyond certain limit, of course, you would experience a loss of the feed, and of course, the whole aspect of introducing vibration is not straightforward. So you need to have sufficient sophistication associated to your screening table in order to achieve the right amount of vibration. So you cannot easily play around with vibration, but vibration, similar to feeding and the screening process, it ensures sufficient amount of interaction is achieved when by both the particles and the surface of the screen. So vibration, it ensures that irrespective of the size and the shape, the particles, they reach the surface of the screen and they are allowed to interact with the surface. When you consider surface, we have both the wires and also the perforation. This vibration helps the particles to interact with both the wires and the perforation, more importantly. So vibration also contributes, or vibration also increases the probability of interaction that ultimately contribute to the process of screening. However, like all these other factors, like the decreased amount of feeding and the decreased angle of inclination, vibration also needs to be regulated, but not as much as the feeding rate and the inclination angle, because vibration often it plays an advantageous role, and vibration involves, or it requires, sufficient sophistication for the screening table, and beyond certain limit, there one limitation or the restriction that is posed by the vibration is beyond certain limit, the amount of or there is a loss in the feed that you provide, and also the damage to the screening surface also increases when you increase the vibration above certain limit. But usually those limits are not often reached on an industrial scale. So therefore, when compared to both these, the feeding rate and the inclination, vibration is more advantageous for increasing the probability of interaction. So what essentially we have seen is we have seen three different ways of increasing the probability of interaction so that the efficiency, or so that the screening is efficiently done. So we will continue this discussion in the next lecture, wherein we will try to see why these factors, or how these factors play a role in efficiently bringing about the screening process. Goodbye.